Let's talk about statistics. Let's talk about statistics and you. Welcome to the wonderful world of math. We're doing statistics. Now, today we want to talk about discrete random variables, and specifically the mean and standard deviation, right? That's what our title says. So let's recall from the past that a variable x is a random variable if its values are numbers, first of all, and that the value of x is determined by the outcome of a probability experiment. So x is random. Further, we say x is a discrete random variable if the possible values are finite or at least countably infinite. And for the purposes of introduction, we're just going to use finite examples for now. But they have to be something that you can list, something that can be put in an ordered list. So, we want to talk about the mean. If you want to see more examples of this, the mean of a discrete random variable is essentially the same as the expected value. And so you can see our video on expected value. We're going to do mean because it's going to help us do standard deviation in a minute. So mean, mu sub x, the mean of the discrete random variable x, is going to be the sum of all of the products x times p of x. That is, we take the value of a variable and multiply it by the probability of getting that value, and then we do that again and again and again, and we add up all of those products. So that's what we're going to do, right? Okay, so p of x is the probability that the variable takes on the value x. That is, if I say p of lowercase x, it means the probability that the variable equals the value, right? We're going to say this for short, but it means that the probability that the variable equals a certain number. Now, our first example here has a recent survey of 600 residents of Bananaopolis, aged 18 to 25 years old. They were asked how many pairs of Crazy Town brand banana pants they owned. The probability that a randomly selected respondent in this age range owns X pairs of banana pants is given below. Find the mean. So here we have a probability distribution, right? The possible values of the variable: nobody owns more than 4 pairs of banana pants. Of course, nobody owns less than 0 pairs of banana pants. You'll notice that all of these things add up to 1, that all of these are between 0 and 1. So this is a probability distribution. We can use this to find the mean according to our formula here. Mu sub x is supposed to be equal to the sum of the products x times p of x. Well, what does that mean? That means that you're going to take each value of x and you're going to multiply it by the probability of getting that value, right? So 0 times the probability of getting 0, 1 times the probability of getting 1. And you keep doing this. And I'm going to run out of room real fast because this takes a long time to write. A lot of space, all that stuff. 0.24, and then plus, maybe I'll make it. Ooh, there we go. This is x times p of x, 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 and then we add them all up. That's what capital sigma stands for, right? Sum, adding the things. So in order to do this, usually what we do is we help make a table slightly bigger, and because we know that we're going to have to add up a lot of things, we're going to make a column for those products, and then we can add that up. So let's make that column. Obviously, the first 2 rows are going to be easy. 0 times anything is 0, so we're going to get 0. 1 times anything is that thing. So there's that. 2 times 0.3 is 0.6. That one's also easy. 3 times 24 is 72, and then the last one is the hardest. 4 times 1.667 is, you can check it yourself, this. Now, those are the same products here. I've just written it differently. In the future, if you want to organize this work on, say, like a test paper or a homework paper, you don't have to write it out like this. I want you to understand that this means this, but organizing it in this table is fine. That is sufficient if you know what you're expected to do. So then the next thing we need is the sum of all of these things. So you've got a list, and you've got a second list, and then you have a third list that is equal to the product entry by entry of the first 2 lists. List 1, list 2, and then list 3, which is, as we said, the product of list 1 and list 2, entry by entry. So our mean is going to be the sum of these things, the sum of list 3. When you add them up, you should get 2.22, approximately. Approximately? No. Exactly, and that's actually really nice. So this is the mean. What does this mean, the mean? This means that if you randomly selected one of these survey respondents repeatedly, in the long run, you would expect them to own 2.22 pairs of banana pants. Crazy town banana pants. So the more we randomly select respondents in this age range, the more we expect the average number of the sample to get closer and closer to the population mean average of 2.22. And in general, as we increase the number of repetitions of a discrete probability experiment, the more the sample mean gets closer and closer to the population mean, the one that we calculated using the formula. So now let's try our second survey group, 600 aged 26 to 33 years old, residents of Bananaopolis, were asked how many pairs of Crazy Town brand banana pants they own, the fabulous banana pants. The probability that a randomly selected respondent in this age group, 26 to 33, owns Y pairs of banana pants is given below. So now we have a new random variable Y, 0, 1, 2, 3, 4 possible values, and the probabilities of each of those values. Find the mean again, right? So this time I want you guys to try it on your own. Try to find mu sub y. So you haven't already paused it, go ahead and pause it and try to calculate all this stuff. 3, 2, 1, let's see how you did. One of the things I suggested you do was you make a third column that has y times p of y, because those are the products we're going to need to add up. So we should get 0, 0.2, 1.0033, and we've got 0.79 and 0.02. Marvelous. So when you take these things and you add them up, you should get, what did we get? We should get 2.01333333, which we're going to round to 2.01. So that as we pick more and more respondents of our survey aged 26 to 33, the more likely it is that the average of this sample is going to be 2.01 pairs of crazy banana pants. Okay, standard deviation. The reason we had to make a new thing here, standard deviation of the discrete random variable, is given by sigma sub x. Square root of capital sigma, the sum of these products. Now this looks similar to what we had before, but this now says x squared times p of x. X squared times the probability that the variable is x. We're going to take all these products and we're going to add those up. And then once we're done with that, we're going to subtract the mean squared. And then we're going to take the square root. Whew, okay. This does not really look like the standard deviation formula you may have experienced in the past. This does look like the computational version of the old standard deviation formula. Here is an alternate, algebraically equivalent formula that should look a lot more like the old one. We're going to use the computational version rather than the conceptual version because we're going to do computations. So they are algebraically equivalent. You should probably check at least one time that these and these give you the same answer, but we're going to practice doing this one. So we're going to need to take the sum of a bunch of these products. So you think it might be helpful to have these products in a new column on our table. So here is the 18 to 25-year-olds. Find the standard deviation. So let's say I made you do the last question about finding the means, and you have this table from before, and you want to find x squared times p of x now. Notice that you can take x squared and then multiply it by p of x, but algebraically this is the same as finding x times p of x and then multiplying that product by x. Because of the associative property of multiplication, whether I multiply these two first and then this, or multiply these two first and then this, it doesn't make a big deal. So if we have x times p of x, and you're doing this by hand, you can multiply x times xp of x and get this. Okay? So go ahead and fill out the rest of the column. 3, 2, 1. Boop. Okay. Now, the standard deviation formula said sigma was going to be the square root of the sum of x squared p of x minus mu sub x squared. So we found mu sub x in the previous example. We need mu sub x squared. We have these products. We need to find their sum. So that's two things we need to do. What do we get when we add up all the things in this list? Check it out. 3, 2, 1. It should be 6.26. And the square that we need here, the square of 2.22, the square of the mean that we found in the previous example, was 4.9284. That is the mean squared. And when we take the difference, we get 1.3316, and when we take the square root, we're going to get approximately 1.1539. You should check that all of this is going to work out, and when we round this to 2 decimal places, we'll get 1.15. Now again, if you're working with these as lists, you see this was list 1 and this was list 2. This, we said list 3 was going to be list 1 times list 2, entry by entry, right? But this new one, our fourth list, we said could be the product of list 1 and list 3. That is, you take this times this, and that's how we got this. This times this and get this. This times this and get this. This times this, etc. Right? That's the easiest way to do it based on what we have calculated so far. With the help of a calculator, you could also say, though, that this was going to be list 1 squared times good old list 2. This is the version here where we said x times p of x, and then we're going to multiply that by another x. And this one over here was where we said we were going to take x squared and then multiply by p of x. So you can take your pick, whichever one's easier. Given the table that we made in the past, this one was easiest to do this way. What does this mean here? This standard deviation, like before, is a measure of how spread out the data are. So that's to say that on average, the number of pairs of Crazy Town banana pants that a resident aged 18 to 25 owns is, on average, 1.15 pairs away from the mean. Your mission, should you choose to accept it, is to find the standard deviation of the second age group. So given what we had before, find sigma sub y. 3, 2, 1. Let's see if we did it right. I hope you gave yourself enough time. This is your last warning. Okay, I know I already counted down. I'm joking. Sigma sub y relies on the square root of a bunch of stuff. The first thing we're going to do is find this column, right? 0 times 0 is 0. 1 times 0.2 is 0.2. 2 times this is going to be 2.0067 because this was an approximate value in the first place. If you do this correctly from the beginning without the rounding, you're going to get what you should here. And then this is going to be 2.37 and 0.08. Okay. If it makes you feel better, yes, looking at this, boom times boom is going to be boom. But then if we're going to do this exactly the way it appears in the column without pretending that it came from a previous example, it did, then we got to fix this, which means that this is also not going to be 0.66, it's going to be 0.0068. And this one is gonna, you gotta fix all those things. It's not gonna make a big difference in the end because we have to round so much at the end anyway. So if we take each of these guys as literal truth, then this column looks like this and this column looks like this, which means that the standard deviation here is going to be the sum of y times p of y times another y, or y squared p of y, minus mu sub y squared, right? So this is the sum of our fourth column there. The sum of the fourth column minus the mean squared. So we square that, and we subtract those, and we take the square root of that, and we get approximately 77.66. So if there was confusion before about how we rounded this to get these things and all that, you can't actually get these probabilities from a survey of 600 people exactly. So where they came from was a number of people, right? And then when you don't round those things, you get approximate values that to the fourth decimal places look like this. So rounding at the end only, like a calculator would do. That's what you should get. And you'll notice that that changes the mean a little bit, that this goes on forever instead of ending. And these figures change just slightly, but to four decimal places, this is exactly the same actually. So the standard deviation of this set, of this age group, is 0.7766 or 0.78 to two decimal places. That means, just like it did for standard deviation in the past, that this data set is less spread out. Smaller standard deviation means less spread out than the 18 to 25 age group, where the standard deviation was 1.5 standard deviations, 1.5 pairs of banana pants, more or less than the mean on average. So this is how we do the standard deviation. We got the values of the variables, we got the probabilities, we take y squared times p of y, we add up all those products, and we subtract the mean squared, and then take the square root. The last thing we wanted to say is that the variance is just the square of that, which means that if you're doing this by hand, you're not going to take the square root and then square it. You're going to do the much easier thing. You're never going to take the square root in the first place. If you're doing this by hand, the variance is easier to do. Here's the formula that looks like the computational formula that we've been using, and this is the alternate formula. So we used this one. Practice it. Our constellation of the day is Circinus, the compass. Not the compass like, where's north and south? No, the compass like the tool geometers use for drawing circles. And this has been a Badger Bear production of the wonderful world of math.